Good morning, students. Today we are going to conclude the titration. That is the volumetric analysis. You remember very well, we have started with definition of titration, uh, the apparatus used in titration, and also we have looked at indicators, and some other things. So today we are going to look at how to record in titration, your table of values. Okay, how to plot the table of values using the first title, rough first and second title, and how to calculate to know the title value that can be used in averaging, that is the volume of acid that can be used in averaging to calculate the title value. We are going to look at that. Also, we are going to look at how you can use titration and to calculate molar mass, percentage water of crystallization, and acid base titration. So these are what we are going to look in this particular topic as we explained below. Now we shall now look at recording in titration. Previously, you have I've introduced you to titration, volumetric analysis, the apparatus used, and some other things. So now to look at how we record in titration. Okay, so titration work could be recorded. First, we have like 4 ways of recording titration results. Now the first one is to state the size of the pipette used in CMQ. So the pipette that you use, the pipette is used to transfer base. So you must state the size of pipette used, because in the exam, pipette can either be 20 centimeter or 25 centimeter. So you must state the one that is provided for your school. So the second one is name the indicator used. So indicator used will depend on the reaction, whether you are titrating strong acid or weak acid. So you must tell us the indicator used in the reaction. Okay, that is number 2. Number 3 is record your titrations in tabular form as shown below. So you record your titration table, okay, in this format. This format that is accepted, generally accepted. You tell us the break reading. The first is rough, first title, second titration. Some people will have third titration, but if you can have rough, first titration, second titration, it's okay. Okay. Now the first thing will be final break reading, initial break reading, and volume of acid used. Okay. So this is how the table of titration look like. Okay. So you tabulate your table. So having done that, the number 4 is you have to find the average volume of acid used. So after you have inputted your values for final break reading, initial break reading, after titration, you have to find the average volume of acid used from any 2 or more title value that do not differ by more than 0.2 cm3. Now, if you have your values, okay, the volume of acid used, the one that will be used for the volume of acid used that we call title value, the difference between the two must not be greater than 0.2 cm3. It must be within the. I'm going to set an example for you to see how this works. So look at the example. These are examples to illustrate title values to be used in averaging. Okay. Now, if you look at this one, we have this particular table. We have break reading, final break reading, initial break reading, and volume of acid used. So after subtracting the initial from the final, you have the volume of acid used for the rough 24.4 cm3. For the first title value is 24.35, and for the second title value it is 24.30. So from this, if you subtract 24.0 minus 24.35, okay, it is the difference is within 0.2. So any 2 title values from this 3 can be used, because their difference is less than or equal to 0.2. So you can use 24.40 plus 24.35 and divide by 2, or possibly you can use the 3 of them and divide by 3. Okay. So since their differences is less than 0.2 and 0.2 cm3, so the volume of acid used, the 3 of them can be used. So now let's see the second one. Now look at this table. the volume of acid you have 25.60, 25.20, and 25.50. So now the 25 point, the only the rough and the first title values, the rough and the first title value are good enough to be used in averaging. So the rough and the first title value are good enough to be used in averaging. So if you look at the first one, 25.60 minus 25.20, the difference is 0.4, as it is above 0.2. So the rough and the first title value can never be used for averaging. When you look at 25.60 minus 25.50, it is 0.1. So that can be used. So 25.60 plus 25.50 divided by 2 can be used. Okay. So the 25.50 minus 25.20 can never be, because the difference is 0.3. So you can only use the rough and the second title value that can only be used in averaging in this table. So let's look at the last one. This one, the volume of acid used from each of them. No two title values can be used in averaging. If there is no title value, you can't, from your experiment, there is no, you can't get title value from the average volume of acid used. That means you need to perform another titration. So that is that. Now you can now come back to calculation. Okay, you have done part of the calculation where you have to calculate percentage purity. So today we are going to look at how you can use titration to calculate molar mass, water of crystallization, and redox titration. So volumetric analysis can be used to calculate the molar mass of a metal, acid, or base. It can be used to calculate the number of moles, number of molecules of water of crystallization of a hydrate salt that contains water of crystallization. We call it hydrated salt. We also use to determine concentration of species undergoing oxidation or redox. That is redox titration. It came out last year. What they brought was redox titration. So now let's now see determination of percentage of water of crystallization in a substance. Let's how we can calculate percentage of water of crystallization in a titration. Okay, so now you are going to follow this step. Hydrated salts are sometimes used in volumetric analysis. What are hydrated salts? Salt that contains water, water of crystallization. Okay, they are called hydrated salts. So, however, you noted that during the titration process, only the anhydrous part of the substance is usually neutralized. The water of crystallization remains in solution just like an impurity. Yes, during a titration, it is the anhydrous salt that is reacting, the one that doesn't contain water. The water of crystallization remains in solution. Like in the impurity reaction, we consider that it's only the pure substance that is reacting. Okay, so put that at the back of your mind when you are calculating. It's only the anhydrous salt, the one that doesn't contain water of crystallization, that is reacting. So let's say a typical example here. A is a solution containing 6 grams per Genk of hydrochloric acid. So they are giving you concentration of hydrochloric acid here, but you are being given in 6 grams per Genk. B also contains 12 grams of hydrated sodium triisocarbonate 4. So these are the compound hydrated salt. Sodium carbonate plus XH2 is the hydrated salt. So the mass of the hydrated salt is 12 grams. You are given the mass of the hydrated salt. So let's continue. A student titrated 25 Genk portion of B, that is the volume of base, with A using methyl orange as indicator, and found above that the average volume of solution A required was 13.10 cm3. Now, if you have to perform an experiment, you are the one that will determine the data value. But here, because we are doing this question is like a theoretical question, so the experiment has already been performed for you. So and the data value has been given to be 13.10 cm. So from the result, question 1, you have to write a balanced equation of the reactions. Question 2, from figure 1, you have to calculate the concentration of anhydrous sodium carbonate in solution B. And number 3, you have to calculate the value of X, and hence the percentage of water of crystallization in solution B. So let's see how we go about each one of them in detail. So solution. Question 1, you have to show equation of reaction. The reaction is between HCl and hydrated sodium carbonate, and this is it. HCl reacted with hydrated sodium carbonate plus SH2. We don't know S, we don't know the number of S, okay? And at the product, you have sodium chloride plus water plus SH2O. That is the XH2O, that is the hydrated salt there, plus CO2 that is giving it. So this is the equation of reaction for that particular equation. So question 2, figure 1, we have to calculate the concentration of anhydrous sodium carbonate in solution B. That is concentration of B, base, in mole per GN is unknown. So mass of conc of A, mass concentration of A, we are given in the question, is 6 grams per GM cube. So we will now convert this mass conc of A to molar conc of A. Okay. Now and by using this formula, molar conc of A is equal to mass conc of A over molar mass of A. So since we are needing the A is HCl, so we calculate the molar mass of HCl, which is H is 1 plus Cl is 35.5, give us 6.5 grams per mole. So from there we insert our value. So molar conc of A is equal to mass conc, which is 6 grams per GN cube divided by molar mass, which is 36.5 grams per mole. So from there molar conc of A will be equal to 0.164 mole per GN cube. So for what we just did was just to convert the mass conc that we were given in the question to molar conc. That's just what we did. The question asked us to calculate the molar conc of B. So we then use this formula. CAVA over CBVB is equal to NA over NB. So now CA is equal to, we have calculated it already, 0.164 mole per GN cube. VA, volume of acid use, lighter value, we have been given 13.10 cm cube. CB, concentration of base that we are looking for unknown. VB is the volume of the base, and it is 25 cm cube that we have pipetted. And NA, from the equation of reaction, the quotient of acid is 2, while the NB, quotient of base, is 1. From there, you inserted your value, and your CB, quotient of base, is equal to 0.043 mole per GM cube. So you have solved the first question. So the second question now asks us to calculate value of X. So using this formula, molar conc of B. So value of X, because X is attached to the base, sodium carbonate dot SH2O. So you calculate the molar concentration of B. Molar conc of B that we have known is equal to mass conc of B over molar mass of B. So what we want to calculate here, we want to calculate the molar mass of B. Okay, so the molar conc of B that we know, we have calculated it to be 0.043 mole per GN cube. The mass conc of B, you have been given the question to be 12 grams per GN cube, and molar mass of B will now be equal to mass conc of B over molar conc of B. From there, molar mass of B will give us 12 over 0.043. That is, molar mass of base now will now be equal to 279.1 grams per mole. So from there, the base is sodium carbonate dot SH2O. We equate it to the molar mass, which is 279 approximately. And from there, sodium is 23. That is 2 times 23 plus carbon is 12 plus oxygen is 3 times 16. Okay, so plus water 2 times 1 plus 16. Oxygen is 16. X is outside because it's XH2O. After calculating that, at the end you have 106 plus 18x is equal to 279.1. From there, we'll collect light 10. 18x is equal to 279 minus 106, and 18x is equal to 173.1. So x at the end will give us 10. So the value of x is now 10. So the formula for the base now equal to sodium carbonate dot 10 H2O. So we have calculated the value of x. Lastly, we have to calculate the percentage of water of crystallization in solution B. Percentage of water of crystallization. So you're supposed to know how to calculate percentage composition. So percentage of water of crystallization. This is the formula that I'm going to use. So the formula is concentration of hydrated salt minus concentration of anhydrous salt times 100. Everything divided by concentration of hydrated salt. So percentage of water of crystallization is equal to concentration of hydrated salt we have been given in grams is equal to 12 minus concentration of anhydrous salt we have calculated it to be 4.56 times 100, and everything divided by concentration of hydrated salt which is also 12, and percentage of water of crystallization is now equal to 60.0%. So this is how to calculate percentage of water of crystallization, value of x using titration. So in our next class, we are going to be looking at organic chemistry.